Hello everybody, this is Dr. Christopher White, and in today's presentation we are going to be looking at minerals. Alright, let's get going. So in front of us we have the classic definition of what a mineral should be, or more accurately, the 6 criteria a substance has to meet in order to be considered a mineral. Now these are the classic criteria, so these are the ones that you've probably seen before in earlier courses. So the 6 criteria, of course, naturally occurring, has to be homogeneous, has to be solid at room temperature, so that means 25 degrees Celsius and 1 atmosphere pressure. It has to be inorganic, it has to have a defined chemical formula, and it has to have a crystal lattice, so that means the atoms in it have to be organised in a repeating pattern. So these are the things that a substance has to have to be considered a mineral in the classic sense. So, do these 6 criteria actually hold up in the real world? Yes and no. So we can see that a few of them do have issues, so naturally occurring, bit of a problem there, solid at room temperature, big problem there, inorganic, massive problem there, defined chemical formula, little bit of a problem there. Homogeneous and has to have a crystal lattice, they're both absolutely fine, they hold true all the way through. So okay, so now let's go through each of the criteria one at a time. We're going to kind of see, where the problems come from. So the first one is naturally occurring. Now naturally occurring hasn't been an issue for a very, very long time. The problem is that we're at a point now where we're starting to produce lab-grown minerals. Some of them natural, some of them artificial. So, if you've ever been into a jewellery store and you've walked around, you might have seen jewellery that contains, surprisingly large things like emeralds and sapphires at a surprisingly low price. Given the size and quality of the gemstone in the necklace or the earrings or the ring. And this is because the crystal that you're looking at is not natural, it's produced in the lab, and so it can obviously be found and obviously produced at a much, much lower cost compared to a jewel that has to be mined out of the ground. So obviously we have a bit of a problem there. So we've got natural minerals which are now being produced in the lab. In all other sense, that emerald that's been produced in the lab is exactly the same as an emerald that's been dug out of the ground. The problem is, of course, it's not natural. It's been produced by a machine. So you have the first question of, it's still an emerald. Surely it should count as as a natural stone. And then we come on to artificial minerals. So in lasers, if you're ever lucky enough to use a laser, I would advise it. It's great fun. If you ever use a laser, a very high power laser, part of it will be what's called a yttrium garnet. So yttrium garnet is used as part of the laser. It's referred to as YAG. Now yttrium garnet isn't really a naturally occurring substance. However, the substance itself, this yttrium garnet, is in fact, once again, it meets all the other criteria of being a mineral. So the question is although this doesn't occur in nature, could you argue that this could possibly be considered a mineral? It meets all the other criteria, just falls down on one of them. So at the moment the answer is no. These crystals are still not considered to be minerals. However, bearing in mind that there are lots of minerals out there that don't meet one of the other criteria, you could argue that given time there is a chance that these lab produced minerals may well start to be considered reasonable for inclusion as minerals. Okay, so that one's a bit of a problem, not really a problem yet, but there is the possibility that things might change in the future. Next criteria, homogeneous. Now that one's completely safe. If the crystal you're looking at is not one solid phase, then you can't classify it as a mineral. Because if it's 2 different phases, then it's 2 different minerals. So that one easily taken care of. Okay, solid at room temperature, so 25 degrees Celsius, 1 atmosphere pressure. Well, there are 2 minerals that fall down on that particular point, and they are mercury and ice, which we know at room temperature will of course be liquids. So the question you're asking yourself is, well, okay, why do we consider them to be minerals? And the answer is quite straightforward. We considered them to be minerals before we kind of came up with the classic definition of what a mineral should be. And so in order to avoid, large arguments, they were grandfathered in. So we just said, okay, look, we know they don't meet this particular criteria, but everyone considers them to be a mineral, so let's just shove them in and we'll all be happy about it, and we can all go to the pub. Done. And that was pretty much the attitude with that. So all other minerals that I can think of off the top of my head will be solid at room temperature, with the exception of mercury and ice. Okay, inorganic. This is the really, really problematic one. So in order for something to be considered organic, of course, it has to include carbon. And so that's a bit of a problem. So if something includes carbon, it must be considered organic. So the question then becomes, what about diamonds? They're nothing but carbon. What about abelsonite? That contains carbon right here. What about the carbonate minerals? Okay, calcite, dolomite. So we have ourselves a bit of a problem there, don't we? So inorganic has now been changed to non-biogenic. So what we're saying is the carbon in a mineral is not being produced through a organic process. Okay, so the diamonds are being produced through the combination of heat and pressure on a material which contains some carbon. So there's no organic process involved in that. It's just purely pressure and temperature controlled. In contrast, if you start to think about things like protein crystals, which are produced by bacteria, well, those crystals, they are natural, they're homogeneous, they're solid at room temperature, they have an organized crystal lattice, and they are, can't remember the last one. Oh yes, they have a defined formula. That was it. But obviously they're produced through a organic process, and so they cannot be considered to be a mineral. So inorganic has now been replaced by non-biogenic. Okay, on to the next one, which apparently I just forgot a second ago. Yeah, good work, me. We next have defined chemical formula. So when we think of a mineral, we think that it has to have, this nice, neat chemical formula. So something like quartz, SiO2, done, solid. Now, over time, what we've begun to realize is that lots of minerals actually have quite variable compositions. And the classic example of this is the mineral olivine. So up here we have the chemical formula of olivine. We have magnesium and iron, silicon and oxygen. You notice the magnesium and iron here are in brackets. So the question is, well, why are they in brackets? And the reason they're in brackets is because the magnesium and the iron can substitute for each other in the crystal. They can just swap. And so this means in every individual crystal of olivine, the amount of magnesium and iron will be different. So what this means is we have essentially a range of crystal compositions, and at one end and both ends you will have what's called the end members. So these are the pure iron olivine and the pure magnesium olivine. So pure iron olivine is called fayalite, and pure magnesium olivine is called fosterite. Now these particular very pure end members are actually extremely rare in nature. It's very difficult to get a pure crystal. Most olivine will fall somewhere on the spectrum in between these two end members. So for instance, if we look at a normal olivine mineral and we analyze it, we might get something that looks like this: magnesium 0.8, iron 0.2. So that would mean essentially this particular olivine crystal would be 80% magnesium, 20% iron, and then SiO2. So this essentially shows us the breakdown, the ratio between these two metals in the crystal. And so this range that we have of different compositions is referred to as a solid solution series. That's the technical term for it. So the fayalite and the fosterite will essentially be the end members, and in between we have this range, and that's your solid solution. Okay, and your olivine crystal can have a composition that falls anywhere along that range. And so the idea of a mineral having a very, very solid, very, very robust chemical formula in a lot of instances is not actually totally accurate. There's actually quite a lot of play in what the chemical formula can actually be. So yes, this is a defined chemical formula. This is 100% accurate, and this is in loads and loads of textbooks. but it's not kind of, what people were thinking of right at the beginning. Right at the beginning, people were thinking, right, this mineral has a solid composition, something like quartz, SiO2, and that's it. So over time, what we've learned is that this, idea of a completely solid, defined chemical formula is not actually accurate. There's actually a lot of these solid solution series out there. So minerals have very, very variable compositions. And just to show you how this can actually work out, so this is something that actually comes from my PhD thesis. So here we have 3 different minerals. We have kotleuskite, sablevskite, and sudburyite, and you'll see they're palladium minerals, so PD, PD, PD. And they obviously have different semi-metals associated with them. So we have tellurium, bismuth, and antimony here. And so what you can see is the tellurium, the bismuth, and the antimony can all substitute for each other. The palladium always stays the same. And so what you'll see is you end up with this whole range of different compositions. So once again, in this instance, we have 3 different variables, not just 2. And in some cases you can have 4, in some cases you can end up with 5 or 6, and these solid solution series can actually get extraordinarily complex and quite good fun. So yeah, so lots of minerals don't actually have what you could classify as a completely solid composition. There's all this variability going on. The final criteria is, of course, the mineral has to have a crystal lattice, so it has to have an ordered structure. This one is 100% safe. So your crystal lattice has to consist of a regular, repeating, 3-dimensional arrangement of atoms, ions, or organic groups held together by various chemical bonds. So you have to have atoms essentially locked together in a rigid structure. Now, the smallest building block of a crystal lattice is referred to as a unit cell. So think of the unit cell as a brick in a wall. Okay, you have unit cell, and they all stack together to form the crystal. So the lattice is actually a reflection of the mineral's crystal system. And if you look down here, you can see the 6 crystal systems. So you can see, depending on how the atoms are arranged, these black dots represent the atoms. So depending on the angles they're arranged and the distances between each other, you can actually end up with 6 different shapes. And if you have a nice well-formed crystal of a mineral, you will actually be able to see these shapes reflected in the crystal. So that's quite cool, isn't it? You have, the arrangement of atoms, so things that are going on at an atomic level will actually affect how your crystal looks at a macro level when you hold it in your hand, which I think is quite cool. Now, there is also a situation where you have a solid phase, so something like window glass, where you do have these unit cells, but they are not arranged in a nice, ordered, repeating pattern. In this instance, that substance would be considered amorphous because it doesn't meet the criteria to have a nice organized crystal lattice. Okay, so it doesn't really meet the criteria to be considered a mineral. And examples of amorphous material include window glass and, of course, obsidian, which you might know as volcanic glass. So if we go to this slide, what we've got here is the classic silica tetrahedra. Okay, it consists of a silicon atom in the middle here in grey and 4 oxygen atoms around it, and it forms this kind of tripod shape. Okay, anything that includes silicon and oxygen to some degree will typically have silica tetrahedra somewhere in the crystal lattice. And so what happens? Well, if we have something like quartz, and this is a 2-dimensional view looking at 2 different layers of these silica tetrahedra. So one layer is in grey and the other layer is in this yellowish colour. And so what you can see is, although it looks a little bit irregular, these crystals are actually organised in nice repeating patterns. You can kind of see this kind of circle there, you can see it repeated here, and you can see it repeated here. So you can see we have these patterns repeated again and again and again. So this is, how it goes. We have these unit cells, the silica tetrahedra. They are organised in a nice repeating pattern. So that's obviously one of the 6 criteria to be considered a mineral. Now the nice thing is when we actually look at how these silica tetrahedra will stack in 3 dimensions, you'll end up with something that looks like this. So here you go, you can see we have all these silica tetrahedra all stacked nicely, and you'll see naturally you'll have these essentially double-ended terminations. So you'll have a point at one end and a point at the other end. And so do we see that in real life? Well, there we go. Yes, we do. So we get, it's pretty rare, but we do get quartz crystals in some instances where we actually have a termination at both ends. And so what we're looking at here is we're looking at the shape of the unit cell affecting how the unit cells can be packed, and that's reflected in the crystal that you hold in your hand. So if you have one of these nice well-formed crystals, it can actually tell you quite a lot about how the atoms are actually arranged in the mineral. Alright, so unfortunately now we've got to talk about something that's a little bit on the duller end. We need to talk about bonds. So we've got to think about how these atoms are actually held together and how that's actually going to affect the mineral which we have. So the first type of bond is called a ionic bond. And in this instance, what we have is we have an atom that will give one or more electrons to another atom. So you'll have one atom that has, 1, 2, 3 electrons that it's not really using, and you have another atom that really wants those electrons, and so the first atom goes fine, take the electrons, and the other atom goes great, thank you. And so obviously what that means is you end up with one atom that has a positive charge because it's gotten rid of some of its negative charge in the form of the electrons, and you have another atom which has gained a negative charge, so it has more negative charge than it did. So you'll have one atom that's now positive, one atom that's now negative, and obviously positive and negative will begin to attract each other, and the attraction between the two is going to be your bond. So the atom that gets rid of the electrons, gives the electrons away, and begins to therefore have a positive charge, is referred to as the cation. The atom that receives the electrons and therefore takes on the negative charge is called the anion. Now, it's a relatively simple situation, isn't it? Positive and negative, that's what attracts them together. Now, the problem is ionic bonds are actually surprisingly weak because it just relies on an attraction between the two atoms to actually keep them together. So the problem is if you can insert something in between them that, also, let's say, has a negative charge, it will cause those atoms to begin to cause those minerals to begin to fall apart, because the other mineral, or the charge of the other mineral, will begin to disrupt those ionic bonds, and the mineral will simply break down. And the classic example of that is salt. So salt is NaCl. It's a sodium and a chlorine atom. The sodium gives one electron to the chlorine, so the sodium is the cation, and the chlorine is the anion. And when they're just doing their thing in the mineral, that's great. One is positive, one is negative. They're attracted to each other. The mineral, the bond is solid. However, as soon as you put that salt in water, well, the water molecule begins to get in between the sodium and the chlorine ions, and when it gets in between them, it will disrupt the bonds, and the mineral will simply fall apart, which we see as the salt dissolving into the water. So, ionic bonds, yes, they work, but they are surprisingly weak, and you can actually interrupt them very easily and therefore cause the mineral to begin to fall apart. Now, a much stronger type of bond is called a covalent bond. So a covalent bond is going to form where you have two atoms and neither of them wants to give away electrons, but on the other end they both really want electrons. And so what happens in this situation is the atoms go, right, okay, look, I want electrons, you want electrons, but I don't want to give them away. How about we just share what we've got? And so what happens is by sharing electrons, each of the atoms manages to achieve its dream of having all the electrons it wants for very short periods of time, because the electrons are constantly passing backwards and forwards between the two atoms. So covalent bonds can be single, double or triple, depending on how many electrons are being exchanged. 1 electron is single, 2 electrons is double, 3 electrons is triple. And covalent bonds are comparatively strong, because once these atoms essentially lock themselves into each other and begin sharing electrons, well, that's a very difficult thing to split apart. And so covalent bonds are surprisingly robust. So minerals that contain covalent bonds are not going to be easily broken down. So if one of the atoms has what's called a strongly electropositive or electronegative nature, it will cause the electrons to be pushed or pulled towards one end of the bond. Now I'm going to leave that statement for now, and I'm going to in the next slide you're going to see what I mean in the form of some diagrams. It's going to make it a lot clearer than me trying to explain it. And when you have this situation where you have one atom that's very electropositive and one that's very electronegative, it will produce what's referred to as a polar covalent bond. So the electrons will stay at one end of the bond longer than they'll be at the other end. Now the final type of bond is called a metallic bond. And in the metallic bond you have essentially metals, and the outer electrons in these metals are only very, very loosely attracted to the nucleus. So if you look at a lot of the transition metals, what you'll see is the electrons at the very, very limit of the outer shell, essentially they are only very, very weakly attracted to the nucleus. So they in theory they could fall off relatively easily, for want of a better way of describing it. And so if we get a load of copper atoms together, well, what happens is because these outer electrons are so weakly constrained, they just start switching from one atom to another. They're just constantly jumping around between atoms. So what this means is essentially you have these metal ions, these metal atoms, which are sitting in a cloud of electrons. All these electrons are constantly moving from one atom to another. Now, what this means is the atoms are sharing electrons, so for very, very short periods of time, some of the electrons will be slightly negative because they will have gained an electron, and some of the metal ions will be slightly positive because they will have lost an electron for a short period of time. So that's what's holding things together. It's this, positive negative charge combined with, the kind of covalent-ish like nature of sharing all these electrons. And that's what stops everything from falling to pieces. And these metallic bonds, as the name suggests, are found in native elements. So you'll find it in things like gold and silver and copper when it occurs just by itself in the native form. It will also occur in naturally occurring alloys. So this is the mineral electrum, so that's gold and silver. And electrum is actually the primary ore mineral for gold. So electrum is where you find most gold. And so in the case of electrum, once again, you have the gold and the silver are passing electrons between each other, and they are doing that in the form of a metallic bond. Now, the nice thing is about metallic bonds is because they're not very rigid, it means the minerals you produce will often actually be quite flexible. You can bend them. So if you do have native copper and you've got enough strength, you can actually just bend it. You can physically make it bend, and that's because these metallic bonds are just so flexible. It makes life, makes that quite easy to do. So here we go, let's run through our three types of bond in diagram form now. So here we have the ionic bond. In the case of the ionic bond, the atom that doesn't want the electron is perfectly willing to get rid of it, whilst the atom that really wants the electron will happily receive it. And so in this case we have the electron goes from this particular atom and it's donated to this atom, so this atom becomes positive because it's lost an electron. That means it has one more proton than electron, so of course protons are positive, so it means this atom becomes positive. Whereas this atom has now gained an electron, so it has one more electron than proton in its nucleus. So now all of a sudden it's ever so slightly negative because it has that extra electron. And so the bond in between them is a result of the attractive force between the two ions, the positive cation here and the negative anion here, and the attractive force will essentially cause them to hold together. And obviously the closer these two ions can get to each other, the stronger that attractive force will be. Now, in the case of a covalent bond, you can see here are two atoms. They really want to have one electron each, but neither of them is willing to give it up. And so what we have here is a situation where, in the case of a covalent bond, some of the shells, some of the orbits of the electrons around the nucleus will actually merge. And by doing so, they will end up sharing electrons, and what you end up with is a very strong bond because these two atoms are now locked together pretty much. So the bond you produce is very robust. So as I said, minerals that have these covalent bonds will often be extremely strong and very difficult to break down. The final type of bond was metallic, but we don't really have a diagram for that. But the other type of covalent bond was what's called a polar covalent bond. And so you're thinking, what is he talking about? Well, in the case of a polar covalent bond, it's just like a covalent bond over here. The electrons are being shared. However, there are some elements in the periodic table that are very, very strongly electronegative. So they really pull the electrons towards themselves very, very strongly. And there are some elements in the periodic table that are quite electronegative. So they are willing to, give away their electrons, but not completely. They want to hold on to them, but they don't really quite have the force to keep hold of them when compared to the electronegative elements out there. So if we look down here at this periodic table, you can see it's color-coded. So essentially it shows how electronegative each of the elements are. And if you look over here, in the halogens, you can see we have fluorine, chlorine, bromine, iodine. We also have oxygen and nitrogen over here, and you'll see they are very, very electronegative minerals. So if you form a covalent bond with any of these elements here, they're really going to start pulling the electrons towards themselves. And so what this means is, in this situation, this is our electronegative mineral, and this is our electropositive mineral. And so what happens is, although they do share the electrons, because this particular atom here is just so electronegative, it will hold on to the electrons for most of the time. And so this means this end of the bond will become quite negative because it will have the electrons most of the time, whereas this end of the bond will become a bit positive because it will not have the electrons for quite a lot of the time. And the classic example of a polar covalent bond is water. So if we look up here in the top right, you can see here we have water. So we have an oxygen here and two hydrogens here in grey. Okay, and so this grey blob around them is kind of showing the outer shell and the electrons being exchanged between these three atoms. And so if we look at it in a color-coded form to kind of show, right, well, where are the atoms most of the time? Sorry, the electrons, should I say, I do apologise, electrons. What you'll see is we have the oxygen, which is very electronegative, pulling the electrons towards itself. So although these are covalent bonds, the oxygen is keeping hold of the electrons for a lot of the time. And so it's very, very electronegative. In contrast, the poor old hydrogens down here and here, well, although they are covalently bonded to the oxygen, they don't really get the electrons most of the time. So they are essentially electronegative. Electropositive, I do apologise. And so what you end up with is a situation like this, where your molecule has a negative portion and a positive portion. Now this becomes interesting later on when we start talking about the intermolecular forces. But I think I've been going on for long enough, so I think this is a very good time to stop the presentation. So once again, as usual, stop the presentation, get up, have a walk around, go and get a glass of water, take 5 or 10 minutes, and then come back for the next part of the presentation, please. All right.